Hello everybody, welcome back to Measure Theoretic Probability. I just wanted to let you know real quick that during the last video, when I was editing it was quite long, so I decided to cut it off. The things filmed in this video were filmed back then with that material, so if in the video you're going to watch today I reference something from earlier in the lesson, it might actually be in the last video. I promised in this video we would move from random variables to random vectors. And in today's video, I'm just going to talk about a two-dimensional random vector. I don't want you to think about infinite dimensional random vectors for quite a while. And if I describe it for two, you definitely know what it means to have a three-dimensional vector and a four-dimensional vector. So I thought it might be easier to work with two variables rather than a generic k variables. We are staying in the simple random variable mode. So a vector-valued random variable, a capital X of omega consisting of two components, capital X1 of omega and capital X2 of omega, is a function from omega into R2, the two-dimensional reals. It's simple because it takes on a finite number of values, and that's our assumption. And the part two of the definition of a simple random variable, where we pulled back any particular real number, in the actual definition, we didn't pull back the specific AIs. We pulled back any individual x in the reals, and now I'm going to pull back any individual point x1 and x2 from the reals. And if that pullback is in the sigma field curly f, then this is the measurability condition for this simple random variable. It's the definition. So a simple random variable of two dimensions, So a two-dimensional simple random variable takes on a finite number of values, and part of the definition for any little x1 and x2 in R2, if you look at what omegas put through this two-dimensional function give you that point, then that needs to be an f, and that's the measurability condition. That is how we define a two-dimensional random variable. And so let's move on to a sigma field generated by a two-dimensional random variable. The sigma field generated by x1 and x2 is the smallest sigma field on omega, for which the function x1 and x2 that takes points in omega and spits out points in R2 is measurable. And the measurability condition is that pullback condition we just talked about. So we need all the omegas for which x1 and x2 map to any particular point in the two-dimensional reals. We need that to be in the sigma field, and that's not enough to define it. We need the sigma field also to be the smallest. We are going to be able to use a higher dimensional version of the theorem I stated today without proof to actually characterize sets in the sigma field by pulling back subsets of R2 or R3 if we're talking about three dimensions, or R4, etc. Before I go to my next slide, I'd like to point out something subtle up here. I wrote sigma of the vector x1, x2, so I had parentheses and parentheses again inside. Sometimes you'll see it written like this, sigma of open parentheses x1, x2, close parentheses. And that means the same thing, but it really has a different meaning. It's just that they're equivalent. So a lot of times people will totally ignore the distinction. Without the double parentheses, sigma of x1 and x2 is defined to be the smallest sigma field with respect to which each x1 and x2 is individually measurable. So we won't be pulling back two-dimensional points, but pulling back one-dimensional points for each separate random variable. You don't have to worry too much about whether there are two parentheses or one, because I claim that this is equivalent to our previous definition. So let's show that. I have the measurability condition on the previous slide defined in terms of pulling back a two-dimensional point. And now I'm saying we can define it in terms of pulling back just one-dimensional points for each of the components. I'm going to prove the reverse direction first. I'm going to assume, and let's stick with the two dimensions here, I'm going to assume that the sigma x1, x2 is defined as the smallest sigma field for which x1 and x2 are measurable individually. So that means that if I pull back points from R under x1 into omega, that set needs to be in here. And if I do the same thing with x2, that set needs to be in here. So let's assume this is true and get to the two-dimensional pullback. First of all, note that Well, first of all, let's choose a two-dimensional point because I want to show that the two-dimensional pullback is in the right place. So let's take a point at R2. I'm going to call it little x1 and little x2, and look at the set of omegas for which the vector maps to that two-dimensional point. This is equivalent to looking at the omegas for which the first component maps to this point, and the second component maps to this point, but they have to happen at the same time with the same omega. So this is equivalent to intersecting two sets like this. Now, if I'm assuming that this part of the definition is holding for our two-dimensional random variable, then I am assuming that this one-point pullback is in this sigma x1, x2, and so is this one. And if this is a sigma field, the intersection is going to be in there as well. So what we have just shown is that this set, the two-dimensional pullback, is in the sigma of x1 and x2, which is equivalent to the original definition for measurability in two dimensions. But we have to go the other way. So now I'm going to assume the two-dimensional pullback works. That if I take a point x1, x2, little x1 and little x2, and pull them back under that vector-valued function, I will get a set that is in the sigma field F. I will get that measurability condition. So if I look at the set of omega under which capital X1 of omega maps to a little x1, I want to try to write this in terms of what's going on with the vector. I can write this as the set of omega for which the vector x1, x2 maps to little x1 and little x2, but I don't care about the little x2. So I need to union these sets and consider all possible values for little x2 to get down to the condition for the random variable x1 alone. So if I started with the assumption that this is in the sigma field generated by x1 and x2, then the union should be in there as well. With a caveat, we only have countable unions. We only have sigma fields closed under countable unions. Is this a countable union? We're safe here because we are talking about simple random variables. So the possible number of little x2s are finite, not only countable, but finite. So taking any little x1, forming this set as a union of these sets under the assumption that these sets are all in the sigma of x1 and x2, this union is a finite and therefore countable union. And that implies that this individual set is in there as well because it's written as a finite union of sets in the sigma fields. So you can do the same thing with the x2 random variables. So I'm going to end this proof right here. We have essentially shown both directions of that statement. Do you do the vector valued pullback or the individual random variables, pull them back as individual components? It doesn't matter. And so often people use the notation sigma of x1, x2 with extra parentheses in there when they mean pull it back as a vector and no extra parentheses inside if they don't mean that. But a lot of people don't even realize there's a distinction and they're using different definitions. So I don't know if you're going to see even myself use that notation, double parentheses or single parentheses, consistently. Okay, so as a final thing today, I just want to state the higher dimensional version of the theorem I already stated without proof today. We are going to prove it at the beginning of the next video. Suppose that capital X1 through capital Xn is a finite sequence of simple random variables. The sigma field generated by all the random variables consists of all subsets of omega of the form, the omegas that map to a set H, where H is any subset of Rn. So it's a little cumbersome, but we can write this as the inverse image of H under the entire vector. So this is now identical to the old definition with a vector in place of the individual random variable. So this is a way to characterize what sets in this sigma field look like. Now, because these simple random variables take on a finite number of values, either individually or equivalently as a vector, it is enough to pull back all finite subsets H of Rn. And in fact, we're going to see, just like we've done in examples today, that it's probably enough to even pull back less subsets of, but we'll have examples of that next time. And we have number 2 of this theorem. So we have a finite sequence of simple random variables, x1 through xn. We generated a sigma field with those random variables, and we bring in a new random variable, and it's measurable with respect to that sigma field, maybe with respect to the original f as well, but I don't know. It's measurable with respect to the generated sigma field if and only if y can be written as a function from Rn to R. Okay, so let's prove it. Before actually I prove it, I want to give you some shorthand notation that is commonly used in the literature. I don't like to use it, but I use it when I have to, and I think I have to today because some of my slides are going to be a little too busy otherwise. So if you see a set like this, given a random vector x1 through xn, the set where x1 through xn is in H, you don't see any omegas here, but they're there. They're just suppressed. This means the set of omegas such that x1 at omega, x2 at omega, out through xn at omega is in the set H. So sometimes we suppress the omegas, and this is done a lot in the literature, so it's not just me, you're going to see this other places. Now let's prove the theorem. The proof of part I. In part I claimed that the sets in the sigma field generated by x1 through xn had a certain form. So the first thing I'm going to do is define classes, a class of sets of that form. I'm going to let curly M be all subsets of omega of the form the omega for which x1 of omega through xn of omega is in a subset H of Rn for any H in Rn. So running over different subsets of Rn will give you different sets in the class curly M. Now this is precisely what I claimed sigma of x1 through xn was going to be. So our goal is to show that M is equal to sigma of x1 through xn. And we're going to do this by taking 3 steps. Number 1, we're going to show that curly M is a sigma field. Number 2, we're going to show that each xi is measurable with respect to curly M. And the sigma field generated by x1 through xn is the smallest sigma field for which that happens. So number 3, we're going to show that curly M is a subset of sigma of x1 through xn. Now it can't be a proper subset because it's a sigma field with respect to which each xi is measurable, and sigma x1 through xn is defined to be the smallest such sigma field. So if we show that M is a subset of sigma x1 through xn, we're actually showing that M equals sigma of x1 through xn. Okay, so let's prove number 1, that curly M is a sigma field. This is very straightforward. I didn't say easy. It might be easy for you. It might not, depending on where you are in your studies, but definitely it's straightforward in that we have some things to check off, some boxes to check. So number 1, we want to show that omega is contained in curly M. This means that we want to find a subset of Rn such that the set of omegas that map into that subset under the x vector function is actually the full set of omegas. Well, everything in omega maps somewhere into Rn. Now, we don't need to hit everything in Rn, but everything in omega goes into Rn. So let's take H to be Rn. The points in omega under the function x1 through xn that map into Rn is just all the points in omega. So that's how we get the omega set. The second thing we want to show that curly M is a sigma field is that it's closed under complements. So I'm going to start by taking a set A in curly M. This means that there's some subset H of Rn such that A can be written this way. And we want to show that A complement is also in curly M. So we want to find basically the corresponding H set so that we can get A complement written in this way. So I've got a set A over here in omega, and all the points there under the x function, the n-dimensional x function, map into this set H, and none of them map outside, and all of the points outside of the A over here map outside of H. So in other words, A complement over here is going to map into H complement, and that is a subset of Rn, so that we can write A complement in this form. So we have shown that curly M is closed under complements. The third thing is we want to show that curly M is closed under countable unions. So I'm going to start by taking an A1, A2, A3, etc. Out of M. This means that there's sets in Rn, H1, H2, H3, etc., such that each AI can be written accordingly. I want to look at the union of the AIs. So here I just wrote out what AI is. I want to look at the union of the omegas that map into I want to look at the omegas that map into H1, union with the omegas that map into H2, union with the omegas that map into H3, etc. So let's just consider two of them. If I look at the ones that go into H1 and the ones that go into H2, then if I want to union those sets together, those points are going to go into either H1 or H2. In other words, those points are going to go into the union of H1 and H2. So for that reason, although there's more sets here, this union is equal to the set of omegas under x1 through xn, which map into the union of the HI. And the union of the HI is contained in Rn, and so this set, and therefore this set, is contained in curly M, so we have that curly M is closed under countable unions. For part 2 of our steps in the proof of part I of the theorem, we want to show that each xi individually is measurable with respect to the now known sigma field curly M. We're working in one dimension if we look at each of these alone, and these are simple random variables. That was part of the setup of the proof. And this means we don't have to pull back Borel sets or any other kinds of sets. We can pull back single points in R. So I'm going to take any x in R, and I want to look at the omegas that map to x under the function xi, and I want to see that this is in M. How do we define inclusion in M? We get the set into a certain form. So note that the omegas that map to x under the one-dimensional function, the xi, is equivalent to the omegas for which the entire vectors of x map to any subset of n-dimensional points for which the ith point is equal to x. In other words, this set is equal to this set if we define H to be all n-dimensional reals for which the ith component is equal to x. So we're done showing that this is an M, and therefore we have shown that the ith component of a random vector is measurable with respect to the sigma field M. So let's show part 3 of the proof of part I of the theorem. Here's where we already have that M is a sigma field. We have that each xi is measurable with respect to M. We know that sigma of x1 through xn is defined to be the smallest such sigma field. So either M is larger and the sigma of x1 through xn is contained in it, or equal. So what I want to show is that curly M is actually contained in sigma of x1 through xn, and this would force them to be equal because it can't be properly contained in there, or sigma x1 through xn would not be the smallest sigma field such that each xi is measurable. How do we show one class of sets is contained in another? We grab a set from the first class and we show it's in the second class. So let's take a set A from curly M. By definition of curly M, this means there's an associated H that's a subset of Rn such that A can be written in this way. So here is the same exact set, just written with the suppressed omega notation. Note that I can write this as a union of the sets of omegas for which the vector x1 of omega through xn maps to a point in Rn called little x1 through little xn, as long as a union over all of the little x1 through little xn, those n-dimensional points in H, in this H. So I'm working with sigma fields here. I hope we don't have an uncountable union. Fortunately, because we are working with simple random variables, the even if H is probably uncountable, but only a finite number of points are going to be in the range of this function. So this union can be taken over all points that are in H, but restricted to a finite number of values based on what the individual random variables can produce. And they're simple, so finite number. Now, if we use the original definition of sigma x1 through xn, where we looked at pulling back the entire vector as opposed to individual components, I know this set is in sigma of x1 through xn. And because we have a countable and actually finite union here, and sigma x1 through xn is a sigma field, this entire thing is in sigma x1 through xn. So I started with an A in curly M, and we showed that it's in the sigma field generated by x1 through xn, and therefore we are done with the proof of part I of this theorem. Now let's prove double I. Just to remind you, let me throw the theorem back up here again. A simple random variable y is measurable with respect to the sigma field generated by x1 through xn if and only if y can be written as a function of x1 through xn. And this function is going to be some function from Rn to R. Let's prove the forward direction first. I'm going to assume that y is measurable with respect to the sigma field generated by x1 through xn. Because y is simple, it can take on a finite number of values. So let's say k values, and let's call them little a1 through little ak. Let's assume that these values are distinct. We spoke earlier, or maybe in the last video, about how we can always write a simple random variable with distinct ai, and if they're not distinct, you can rewrite it so that they are. If y is measurable with respect to this sigma field, as we're supposing here, that means that the set of omegas that map under y to ai is in this sigma field. Simple random variable, and this is how we show measurability with respect to a sigma field. Now, if this set is in this sigma field, by part I of this theorem, we know that we can represent this set with one of those Rn sets, H. So I'm going to write this set of omega for which y of omega is ai to be the set of omega for which x1 of omega through xn of omega is in some set hi. I'm going to do this for a1 through ak, getting sets h1 through hk, all subsets of Rn. Let's define the function f of x1 through xn, and this is just a function, there's nothing random here, as a sum of the coefficients little ai times the indicators that say that the point over here that you're plugging in is in one of these sets, h1 through hn. So this looks like the way we can define any simple random variable if we're using randomness. There's no randomness, but y of omega is equal to f of this with the random variables x1 of omega out through xn of omega plugged in. Note that this is actually a function, since each x1 of omega through xn of omega, that each point, n-dimensional random point, can fall into only one of the hi sets. Because if capital X1 of omega through capital Xn of omega, that n-dimensional random variable, falls in, say, hi and hj, then that means that y of omega is going to equal ai, and y of omega is going to equal aj. But we said that the a's are distinct, so we can't have this happening, and that's why we know that each of these random points can fall into only one of the h sets. And that's it. We're done with the forward direction of part double I of today's theorem. Let's go the other way. So now I'm going to assume that y is a random variable defined like this. Y of omega is equal to f of x1 omega through xn omega for some function f from Rn to R. I want to show that y is measurable with respect to the sigma field generated by x1 through xn. And this means that I want to show that the set of omega for which y of omega is equal to any particular real number, I'm going to call it y so it matches, but you can call it x, is in the sigma of x1 through xn. One way I might show that this set is in sigma of x1 through xn is to show that it has the form of the sets given by part I of this theorem. In other words, I would like to write this set of omegas for which y of omega is equal to little y as a set like this. And I can if I take capital H to be the set of all n-dimensional points in Rn, such that f of that point is equal to y. So now, by part I, we do know that this, and therefore this, is in sigma of x1 through xn, and we've got that our random variable y is measurable with respect to the sigma field generated by x1 through xn, so we are done with this proof. In the next video, I'm going to start by showing you a cool relationship between the sigma field generated by, say, x1 and x2, and the sigma fields generated by each of those variables individually. And then we're going to move to general random variables and get away from the simple case. And after that, we're going to start talking about convergence of sequences of random variables. It's going to be awesome. So I hope to see you in the next one and beyond.